Welcome to my third lesson on differentiation. In this lesson, I want to take you through stationary points and curve sketching. And let's begin. Stationary points. Stationary points are actually turning points. Those two words there are used interchangeably, or they are synonymous. When you talk about stationary and turning, we mean the same thing. These are points where the gradient, change in y or change in x, is 0. It's a point where the curve is momentarily at rest. That means it's horizontal. It has no gradient. As far as along the y-axis is concerned, we're not going up or down. Now, turning points include the following. There can be a maximum point, which is this sort of a thing here. The curve is going up the topmost part and going down again. Students at this point should be familiar with the fact that when lines flow upwards that way, the gradient is positive. When they slope this other opposite direction, the gradient is negative. And therefore, with that in mind, I need to say that for a maximum point, the gradient before the turning point, the maximum point, is positive, and at the turning point is 0, and after that it's negative. So there's that sequence of plus, 0, minus. The second derivative at the maximum point is normally a negative number. That means if you take the x value at the maximum point, if you take the x value at the maximum point and do the second derivative and put that x value in the second derivative, differentiating twice, and reduce and simplify, it will reduce to a negative number. Again, the second case of turning point is the minimum point, which looks this sort of a way. And of course, it begins with a negative, the 0, and positive after that. Therefore, there's a sequence of minus, 0, and plus. So the exact opposite of this other one. Again, I should mention that the second derivative is normally positive. That is, if you take the x value at the minimum point and put in the second derivative and reduce and simplify, it will reduce to a positive number. The third case of a stationary point is a point of inflection. Now, it can be this particular sort of shape, or this other shape there, and I should say, of course, this will be positive, then momentarily becomes negative 0, and positive after that, or the opposite, begins with negative 0 and negative there, and therefore we have those two cases. I need to mention that a point of inflection really represents some sort of two turns in one. What I mean is that so we have a turn there and another turn there, or we have a turn over there or a turn like that, because you see the graph could have just turned and stopped turning and continued, but it turns and turns again. So we have like two turns in one to represent the point of inflection. I mean, I need to mention that second derivative normally is 0. That means if you take the x value at the point of inflection and put in the second derivative and simplify, you'll actually get a 0, and therefore that is all the turning points that there are. This is a maximum point where the curve goes. This is a minimum point where the curve goes. Now, sketching curves. This means getting the general shape or flow of the curve. And to do that, we need the x-intercept, the y-intercept, and the turning points. We also need to find out the nature of turning points. We shall see that in the second lesson that will be following after this, because it cannot be done in a single lesson. It's too long. Let's turn to actual examples on stationary points. We are told to determine the stationary points, the following curves, and find the nature of each point. So we have those 4 questions there. Let's start with this statement. At a stationary point, we have just said the change in y or change in x is 0. So that's the guiding principle in all of the calculations we're going to be doing. To begin with, we have the question y is equals to 2x cubed plus 5. Therefore, we say the first derivative of this, which is 6x, is actually equal to 0. Sorry, the first derivative of this, which is 6x squared, is actually equal to 0. So we look for the value of x by, first of all, equating that. We get x is 0. Now, since we are looking for turning points, we don't just want the x coordinate, we also want the y coordinate. So please notice that for the same equation, for the same curve there, when x is equal to 0, y is 5. Therefore, the stationary point, therefore, is this point 0, 5. That is the stationary point. We want to find out about what type of turning point it is, the nature of stationary point. So we do it this way. Now we're going to test using the second derivative method, where we take the second derivative and we are finding the derivative of 6x squared, which is 12x. And we say, since at that turning point the value of x was 0, we put x to be 0 here, and putting x to be 0, you're going to have 12 times 0, which is 0. So the second derivative being a 0 means it's a point of inflection. That means the stationary point 0.05 is actually a point of inflection. Alternatively, we could do the question this way. We look for the gradient before 0.5 and the gradient after 0.5, and we see the sequence. If it is positive, positive, 0, positive, 0, positive, or negative, 0, negative, or positive, 0, positive, or negative, 0, positive. And so it will define to us what sort of turning point it is. And therefore, the gradient before 0.5, we are talking about if in the x-axis we have say a straight line like this. Let me draw something for you here. We have a straight line like that one. We have this point here, that's the point 0. We take points before that point. Say this point is negative, that's negative 1, and then there's another point after that, which is the point, say the point 1. Take the gradient between before and after. Now if we do that, and you can always slow the video so that you try it out, I'm going to take the point where x is negative 1, like I have indicated here. Okay, taking the x value just before this, that means to the left of 0, and therefore we look at the gradient before that. The equation for gradient was differentiating these ones was 6x squared, which is this one. Putting x to be negative 1, the answer becomes 6. All right, and that means it's positive. All right, the gradient is positive before our point of inflection. What about after that? We take the point, say the point 1. We take the point 1, we'll find changing x, change y or change x, and putting x to be 1, and again it'll be 6. That means it's positive, it's 0, then positive. That makes it a point of inflection, and therefore it is this sort of a thing: positive, 0, positive. It's a point of inflection. Yeah, and I think that's clear. Another question is on your screen there. We try that again, and let's see. First of all, we need to do the changing y, changing x to get where the turning points are. We say that the turning points where the first derivative is 0, therefore that equals 0. Simplifying that, you get the value of x is 0.5 or 4. Please try that out and see if the answer is right. Now, for the equation that we were given initially, when x is 0.5, y will be 17.75, and again when x is 4, y will be negative 68. Therefore, the point 0.5, 17.75 is the turning point or stationary point. The point 4, negative 68 is another stationary point. Therefore, now we look at the nature of those turning points. We have two turning points at these 2 points here, but we want to find out about the nature of that point, and therefore we do the following. Let's use the second derivative method. So since the first derivative of the equation was 12x squared minus 54 plus 24, find the second derivative by differentiating this further, and it becomes 24x minus 54. Now, putting the value for the first value 0.5, 17.75 turning point, we take the value of x to be 0.5. Of course, it is 0.5. It is 0.5. Put it here, so it becomes 24 times 0.5 minus 54, and the answer becomes 42. Negative 42, sorry. That means that type of turning point is actually a maximum point. In other words, it's this nature here. Remember, I did not look for gradient before or gradient after. You can try that method and see. And the answer will turn out that it's actually a maximum point. Second derivative is negative, should be a maximum point. For the point 4, negative 68, we do the second derivative, which is 24. 24x minus 54, but replacing x with 4, we get 24 times 4 minus 54, which is 96. It's positive, that means it's a minimum point. And so this sort of thing that we should get. We can try and look for the gradient before this. Like for this question, you could get, you can use the number before that would be, say, 0. And after that, you can take 10 and replace on this particular equation and see what gradient you get. And it will come out that it's a minimum point after you test that. We go on again. There's a question on your screen there. we try that also. And so finding the first derivative, you get 5x raised to the power 4 minus 27x squared. That should be equal to 0. The first derivative at a turning point should be 0, because that's a point where the gradient is 0, because the curve is like horizontal line, at least at a point. Therefore, please look for solution for this. Simplify this to get the values of x. I got 3 values: 0, negative 2.3, or 2.3, and because this is x raised to the power 4, that's the highest power, we expect to get 4 answers. But this one here is actually representing 2 answers, because if you factorize out x squared, you get x squared outside, then we have 5x squared inside minus 27 there, all that in bracket. And so solving for that, you get 0 is equals to x squared. That means we have x is equals to 0 is 2 answers. Then these other 2. So that makes 4 answers. Now we're going to test what type of turning points there are. Now I should tell you that whenever we have that kind of a thing, when something is a repeated root like this, it's likely going to be a point of inflection. So maybe that's one indicator that you can always have. Now, turning to the question, this is the question that we're given. And these are the points where we have turning points. We want to get their y-axis counterparts. And so we replace x with 0. Putting x to be 0 in this equation, you get y is 3. And therefore, there's a stationary point at 0, 3. 0, 3. That's a turning point. All right? The next thing, when x is negative 2.3, put that value in the equation that we given there, you get y is 48.2. Therefore, the stationary point at negative 2.3, 48.2. Again, put the value of x to be 2.3 in the equation again and continue. You get y is equals to 42.2. There is a stationary point at that particular point there, and therefore we have 3 stationary points. Now, let's test the nature of these stationary points. The first thing, I suggest you go to the second derivative. So since this was first derivative, which was 5x raised to the power 4 minus 27x squared, differentiate this further, you get 20x cubed minus 54x. And therefore, for the first point, this point here, 0, 3, putting the value of x 0 in this equation, the second derivative becomes 0. That tells us it's a point of inflection. All right? It's a point of inflection. And please test it. Get the value of x before and after, and it will be this kind of a thing here. Okay? But simply, I should say that if you take a point before that, that's like, let's say, negative 1. If this is the first derivative, negative raised to a even power becomes negative 1 raised to an even power is almost like 1. Therefore, this will just be 5 minus 27. The answer is negative. And that means the other one will also be negative. So that's a point of inflection with no doubt there. We go to the second point, which is negative 2.3, 48.2. Testing that again, we put those values in the second equation, second derivative, which was 20x cubed minus 54x. And continuing on, you get the second derivative is negative 119.14. What does that tell us? It's a maximum point. It is this nature: positive, 0, positive. Those are the gradients. It's positive, it's 0, it's positive, negative after that. The last point, we have the point 2.3, negative 42.2. Putting those values, the second derivative, this and here, again, you get positive 119.4. And therefore, that's a minimum point, and it's that nature there. Hopefully, that makes sense to you. We go to the next question. We have this question here. So the first derivative will be 4x cubed minus 24x squared minus 6x. Putting that is equals to 0, you get the values of x is these ones here. Again, since it's cubic equation, we expect to get 3 answers. So we have turning point at the point where x is 0, at the point where just next to that actually, negative 0.2, and then much further to the right of that, which is at the point where x is 6.2. So putting these values in the equation we had initially, we can get the values of y corresponding to 0, negative 0.2, and 6.2. When x was 0, y was 36. Please replace and see if that's true. When x was negative 0.2, y was 35.9. When x was 6.2, y is that number there, negative 508.3. So those are the 3 stationary points. The first one is 0.36, the second one is negative 0.2, 35.9, the third one is 6.2, negative 508.3. Okay? Those are the stationary points that we have. But we have some task to accomplish to look at their nature. So looking at the nature there, we subject them to the second derivative. So the first derivative was 4x cubed minus 24x squared minus 6x. So differentiating that further, you get 12x squared minus 48x minus 6. Therefore, for the first point, this first stationary point, put x0 in this one here. So putting x to be 0, you get the answer will be strictly negative 6. Therefore, it's a maximum point. It's this kind of a thing here. Moving on to the next point, we have the point negative 0.2 at 5.9. Putting the negative 0.2 on this second derivative equation, we have the second derivative will reduce to 4.08. It's a minimum point. And so it appears like this. The curve is taking this sort of a turn. What about the point 6.2, negative 5 or 8.3? So putting the number 6.2 in the equation, you get the answer is 157.68. And therefore, since it's positive, it's a minimum point. Which point is the center here? The point that is at the center is a point 0. So we have 0 at the center. This negative 0.2 is on the left of that, and then we have 6.2 after that. And so let me illustrate something. I'm going to draw a line like this. I'm going to draw a line like that on there. Okay, we have this point here, which is a point 0. Now this other point here is a point negative 0.2. Negative 0.2. And then we have, after that, we have another point, which is 6.2. 6.2. Hey, don't write properly, but you can follow. So we are saying that the curve at the point 0, the curve at the point 0 was, is it a minimum or maximum? It's a maximum. So here, the curve is taking a sort of a turn like that, okay? The curve is turning up that way. And the other 2 points, it is minimum. That means it is kind of going something like that, completing, and then again completing like that. So we have a minimum point over here. That's a minimum point. We have another minimum point, maximum point, and a minimum point. So therefore, you should know that since the curve is the highest power of x is 4, since the curve the highest power of x is 4, it should have 3 turns. It should have 3 turns, and there they are, and in that particular manner. If we had a point of inflection, we would have point of inflection and 1 turning point. That's either minimum or a maximum. So again, the last point there was a minimum point. I suggest that in this case, the second derivative method is superior method than looking for gradient before and after a turning point. The reason is the point negative 0.2 and 0, they are very close. So you'll struggle probably to look for that second derivative. Even when you plot the curve, it doesn't look like it, but second derivative will help you a lot in this particular question. And I suggest that unless otherwise stated, maybe using this second derivative method is a better way of approaching the questions. That brings me to the end of my first presentation about stationary points. After this, or a video that I'll post the same time with this, or shortly afterward, we'll be dealing with how to sketch curves. Having this information in our minds, we should be able to plot curves better. And therefore, I hope you like, subscribe, and share. Thank you.